All right, so today we're doing a deep dive into something pretty wild in the world of AI. And, if we're diving into it, it's got to be interesting. We're talking about the forward algorithm.
And yeah, this is one of those things that's really got people talking, especially because it comes from, well, Geoffrey Hinton.
Hinton, right? Like the godfather of deep learning. This is a big deal.
Yeah, exactly. And his paper is basically shaking up how we think about neural networks. See, right now, everything relies on backpropagation,
Yeah.
but it's the way that neural networks learn.
Right, the backbone of it all.
Exactly. But Hinton's saying, hold on, what if we got rid of that and just went forward?
Just forward, no going back. How do you even learn that way?
Well, that's the ingenious part. Imagine this: two networks running side by side like twins.
Two of them. Okay, I'm intrigued.
One gets the real data, right?
Hey.
Images, text, whatever. But the other, it gets fed what he calls negative data. So think like a distorted image or a jumbled up sentence.
Negative data. How do you even create that? Is there like an AI cynic out there coming up with the most depressing data to feed these things? What's going on?
It's more about creating contrast, right? So you might like blend different pictures together to make these weird mashups or take the network's own predictions and then like flip them around.
So showing the AI what not to do, that's kind of a cool concept.
Yeah. And the goal is that both networks, they're aiming for this thing called goodness.
Goodness. That sounds awfully subjective for an algorithm, don't you think?
Yeah, it's not about morality or anything. It's more about how well each layer in the network is representing the data. Like one way to measure it is by the activity of the neurons. So the more the real data gets those neurons firing, the higher the goodness.
Okay, so it's like a score. High score for real stuff, low score for the weird stuff.
Exactly. And that's how it learns to tell the difference without needing to retrace its steps like in backpropagation.
All right, so this is all very cool and innovative, but does it actually work? Can it really compete with backpropagation?
Well, Hinton tested it out on some classic image datasets like MNIST.
Ah, MNIST. The handwritten digits, right?
Yeah, you got it. But he made it even trickier, using a special version where he scrambled up the pixels
Scrambled pixels. Why make it harder?
to level the playing field. He wanted to force the algorithms to rely just on the patterns, not on where things were in the image.
Ah, so it's like a blind taste test for AI. You can't cheat by using the usual visual cues.
Exactly. And you know what? It did surprisingly well. Like it got down to an error rate of about 1.4%, almost as good as backpropagation.
Wow, no kidding. That's going to be exciting for him. That's like reinventing the wheel and finding out it rolls even smoother.
Right, and it's not a one-off thing either. He also tried it on CFAR-10, which has way more complex images like dogs, airplanes, you name it.
Okay, so we're not talking about recognizing simple shapes anymore. This is the big leagues.
Yeah, and while it didn't do quite as well as backpropagation on that one, what's really cool is the gap between them didn't get bigger as the networks got more complex.
So even with more layers, more depth, it held its own. That's significant.
Absolutely. Especially because those really deep networks, that's where we're seeing the really interesting stuff happening in AI.
Right, right. But I gotta imagine, like anything new, there's still some challenges.
Oh, for sure. One of the early head scratchers was, how do you apply this to recurrent networks?
Recurrent networks. Okay, remind me what those are all about.
So those are the ones that handle sequences, right? Like text where word order matters or like stock prices over time. They've got that built-in memory.
Right, so like predicting the next word you're gonna say is based on the ones that came before it. Context.
Exactly. But this forward thing, it was initially all about those simpler networks. So figuring out how to add in that time element or even spatial awareness, it wasn't obvious.
It's like having a brand new engine, but no clue how to get it into a race car.
Yeah, pretty much. But Hinton, he found a way. He figured out how to treat even a static image, like from MNIST or CFAR-10, as if it were a really boring video.
Hold on, a video where nothing happens. How does that even help?
It's all about giving the algorithm time, you see. By feeding the same image through those multiple time steps of a recurrent network, he's basically letting it learn spatial relationships within the image.
Okay, so each layer is getting input not just from the layer below it, but also from itself at the previous moment in time.
Exactly. Like each layer has a little bit of memory, remembering what it saw in that last frame. And this is what allows for those top-down predictions.
So the higher levels, seeing the whole picture, can make guesses about what the lower levels, focused on the details, should be seeing.
Yes. And then those guesses are compared against the actual input, just like with that real and negative data, right?
Man, that's fascinating. We're talking about an algorithm that doesn't just crunch numbers, but is kind of mimicking how we learn. constantly checking our expectations against reality.
That's a great way to put it, and that actually leads into some of the really big implications of this work. Have you heard of the term mortal computation?
Mortal computation. That sounds a little ominous. Are we talking about AI deciding to pull its own plug?
Not quite. It's more about changing how we think about computing itself.
Okay, I'm listening.
Yeah.
But a little nervously, I gotta admit.
So right now, our software, we like to think of it as immortal, right? Write it once, run it anywhere.
Right, my code should work whether it's on my computer here or on some supercomputer across the world.
Exactly. But that immortality, it takes a ton of energy, a ton of resources to make sure it works on any system.
It's like trying to fit a square peg in a round hole sometimes, just brute forcing it.
You got it. And mortal computation says, what if we embraced the quirks of each piece of hardware?
So custom-tailored software for every machine, like bespoke algorithms.
Exactly. And because the forward algorithm, it doesn't need to know everything about the model beforehand.
It's perfect for that, right?
Yeah,
The hardware itself becomes part of the learning process.
you got it. And suddenly you've got this incredible potential for efficiency. AI that's not just powerful, but runs on whatever's available without needing these massive data centers.
Okay, now that is a game changer. But how does this all connect back to intelligence, to learning in general? You were saying there were even broader implications here.
Well, we've talked about how the algorithm learns, but Hinton also talks about how this could change how we think about transferring that knowledge between AI.
Transferring knowledge,
Yeah,
like copy-pasting information from one AI to another.
it's more like distillation. Imagine you've got an AI that's become a bird expert, right? You wouldn't just copy its data to a new AI. You'd train the new one to mimic the expert's confidence levels in its answers.
So it's not just about what it knows, but how it knows it. Like learning from a master craftsman, not just reading a manual.
Exactly. And that gets to the heart of how we learn, right? Not just absorbing facts, but understanding the why, the how, the nuances. Yeah, and that gets at one of the big questions right now. How do you generate that really good negative data at scale? Hinton, he used some neat tricks for these initial tests, but to make this really work long term, we need something more, automatic.
Right, like a whole nother AI whose job it is to just mess with the first AI. That'd be something.
Huh. Yeah, who knows? But then there's also the question of those goodness functions. We've been talking about measuring neuron activity, but is that always the best way to tell how well the network's doing?
So we've kind of pointed it in the right direction, but maybe the compass itself needs some calibrating.
Yeah, something like that.
Mm.
And it ties into another really interesting thought. You know how our brains aren't just one big blob of neurons, right? Different parts specialize.
Right, we've got the visual cortex, language centers, all that good stuff.
Exactly. So what if instead of every layer in this algorithm trying to learn everything, we could make it more modular?
So instead of one giant factory, you have specialized workshops, each with its own process.
Exactly. That could be huge for making it even more powerful, even more efficient. Maybe even surpassing backpropagation down the line, who knows?
Man, it's wild to think about. It's like we're not just building better calculators anymore, but we're actually starting to understand the principles of learning itself, like at a deeper level.
I think so, yeah. It's still early days for the forward algorithm, but the potential is huge.
Well, that's about all the time we have for today's deep dive. But for our listeners, what's the big takeaway here? What should they be thinking about as they walk away from this?
I'd say stay curious. Don't be afraid to dig into this stuff yourself, ask questions, and remember, AI, it's not set in stone. The most exciting discoveries, they come from people who aren't afraid to think differently.
Love it. It's like we're all explorers out here, and who knows what we're going to find. All right, everyone, that's it for this deep dive. Thanks for joining us, and until next time, keep those minds sharp.